All right, hello, ladies and gentlemen. This is section 5.1, randomness, probability, and simulations. Today, for my activities, you'll use a die, a six-sided number die, and you'll use a penny. Okay, so if your teacher gave you one because you're in class, then great. And if not, go grab one from your closet or your piggy bank, and we will begin. All right, now I'm a McDonald's fan, so pretend for a moment the McDonald's Corporation has introduced a game to attract more customers. For each large French fry, medium soft drink, or chicken product purchased, customers will receive one free game piece. Okay? The McDonald's Corporation suggests in this brand new contest that 1 in 6 game pieces will provide a customer with a winning food item. Okay. One particular customer ordered a 20-piece chicken McNugget value meal where 6 game pieces were provided. The customer found that in his scenario, 3 of the pieces were actually winners. Okay, 3 out of the 6. How likely is this? Okay. Now what we're going to do is we're going to run what's called a simulation. All right. Now when I think of a simulation, it reminds me of the word simulator. And a simulator or like a flight simulator is an artificial event that's used to help represent a real scenario. Okay, sometimes the real scenario is too difficult to do, and for my students, it's not feasible for me to ask every one of them to go out and buy a 20-piece chicken McNugget value meal, even though I think that may be delicious, for a couple reasons. One, they may not have the time for it. Okay. 2, they may not have the money for it because it's probably $7, $8, $9, okay, depending on where you live. And 3, it just may not be the place that you typically buy food, okay, depending on your interests and your health, etc. Okay. So what we're going to do is we're going to do a simulation for buying chicken McNuggets, okay, and we're going to do so one of 3 ways. Okay. First, we have a numbered cube. We'll do that on this PowerPoint slide. The next one, we'll use a random digit table, okay? And then for the third one, we'll use a technology-based random digit generator, okay? And all of them are actually good representations for running a simulation for this particular activity. In the end, you'll oftentimes be asked to do a simulation, and you can choose one of your choice, okay? Now, for this one, we'll use a numbered cube for this particular slide. That's why this is highlighted. And we have 4 steps that our book represents to do. Okay, and the first one is to state the issue. What are we trying to do? We are trying to represent the purchase of a 20-piece chicken McNugget value meal. Okay, and evaluating our 6 game pieces. Okay, and I'll just say that, evaluating our 6 game pieces okay, for our winners. Okay, so we'll look at our 6 game pieces and figure out which ones are winners and which ones are losers. Okay, and we'll do so by, in this case, rolling a die. Okay, and so how am I going to do that? Well, we're going to plan something. And in this case, we'll use blue. To plan, what I have to do is decide amongst my 6 sides which side would represent a winner and which one represents a loser. Okay. Now keep in mind that 1 out of 6 game pieces are considered winners, which is convenient for our numbered cube. Okay, so I'm going to pick any number out of 6, and in this case, just to make it easy, I'll say 1. Let's let 1, okay, represent a winning game piece. Okay, and then the other numbers on the die which are 2, 3, 4, 5, and 6, represent a losing game ticket. Okay, and so what I'm going to do is I'm going to take my die and I'm going to roll it. Okay, roll a die, and if I roll it once, that represents 1 game piece. Okay, on my entire Chicken McNugget value meal, I actually have 6. So I'm going to roll my dice, my die 6 times. Okay, and I'm going to record the results. And know that because each outcome is independent from the next, okay, that repeats are okay. Okay, so you'll roll your dice, record a result. Roll your dice, record a result. Do it 6 times. I've actually already done this, okay? And for now, I'll just tell you what I got. I got a 2, I got a 1, I got a 4, I got another 4, I got a 5, and I got another 2, okay? And so once you record your results, okay, and again, knowing that repeats are okay, I did get 2 4s, that's fine. Also got 2 2s. We're going to count the number of successes. And in this case, count the number of 1s. Okay, so I count the number of 1s, and in this case, I just have 1. 1 out of 6. Okay, and we are good. Okay, and so we'll note that, and hopefully everybody else in the class did the same thing, and they'll have their own unique counts for the number of winning game pieces they had out of 6. Okay. Now, if you were to do this with a random digit table, okay, it would be very similar. Okay, the first part, the statement will still be the same. Okay, so I'm not going to write the statement again, but the plan will have to look a little different because I'm not really rolling a die anymore. Okay. With our random digit table, let's just choose a random digit a line, and we'll say choosing, and I'm just making this up. Typically in your directions, they give you a line to work with. I'll just say 105. Okay, we'll choose line 105. We will let, still again, a 1 be a winner. Okay, and then we'll let 2, 3, 4, 5, 6 be losers. Okay, and again, we're going to choose 6 single digit numbers. Okay, 1 through 6. I'm sorry, that's tough to read. 1 through 6. Okay, where repeats are okay. Okay, however, I have other values that may not be included amongst either winners or losers, and those are the numbers 7, 8, 9, and 0. So what I'm going to say is values 7, 8, 9, and 0 are ignored. Okay, so I'm going to start at line 105. The first number I see here is a 9. All right, and 9 is supposed to be ignored, so I will ignore that. The next number I have is a 5. A 5 is a loser, so I'll put an L underneath it. Okay. The next number is also a 5. Okay, and again, that is a loser. The next number is a 9. 9 is ignored. The third game ticket is a 2. Unfortunately, that is a loser. The next number is a 9. A lot of 9s here. That is also ignored. The next number is a 4. That is a loser. So we have 4 losers so far. The next 2 numbers are zeros. So I have a 0. That is ignored. Next is a 0. That's ignored. And so is the 7. Okay. And then I have a 6. That is also a loser. Okay. Again, number anything 2, 3, 4, 5, 6 is a loser. 9 is ignored. That's not in our. It's not a winner or loser. Okay. And then we have another 9. Not in our group. 7 is also ignored. The last is a 1. That is a number that would work, and that is actually a winner. Okay, so I would record 1 winner amongst all my random digits. And again, I have 6 here that I chose from this line 105. And again, I only had 1 success, okay? Which is good. I feel bad that it came on the last one. It made me a little nervous there, but it did come, so. All right, the last one is using your random digit generator, okay? And so, again, your statement's gonna be the same, okay? Your plan's almost exactly the same. I'm gonna put the directions up here so we can see. Let 1 be a winner. Okay, a winning game piece or a winning ticket. Okay, and then 5, 6, 7, 8. Sorry. Oh, I got that high. Let me take these off, sorry. Okay, then we'll let 2, 3, 4, 5, 6 be a loser. Okay, and that's really, I'll say a loser game piece. Okay, that's really all I need to do for my random digit table. Okay, because sorry for my my technology, my random digit generator, because you don't have to have it evaluate values past the number 6. Okay, or have those items be considered within your pool of numbers. Okay, so here's what I do. I'm going to use repeats are okay. Pick 6 random digits. Okay, and you can say single digits if you want. Just be a little bit more clear. It's up to you. 1 through 6. Okay, and remember, repeats are okay. Okay, and then what we'll do is we will count the results. Count the winning tickets or game pieces. Okay, now here's the command that we do for it. If you don't remember, we're going to go to math. Okay, and then you're going to scroll over a couple topics on the top, go over to probability, and then you got to go down 5 to random integer. Okay, and so here's what you see if you have one of the newer technologies. Okay, so it's random integer, you have to plug in the lower bound, the upper bounds, and then you can put all 6 in, okay, because these are independent. It's okay to put in all 6 because numbers can repeat. I'm going to move my screen up here. Forgive the S being gone, sorry. Some of older calculators will just have you write this part will be printed in the beginning. Let me write this in. Some of the older calculators will just have that with the first parentheses, and you just type in the 1, 6, 6. If you don't know where the comma is, it's 1 button above the 7. Okay, so just above the 7. And then when you close it and you hit enter, this is just coincidentally what I got. Okay, and again, in this one situation, I had a single value winner. So I had 1 winning ticket. Okay, 1 winning game piece out of 6. Okay, and there it is right there. It's that 1. Okay. Oddly enough, I think I got one of each digit in that particular sequence, but it was just, or that results in, that's just kind of a fun coincidence. So you probably got something different at times. So there's no set number that you should always get, meaning you won't always get a 1. Sometimes you'll get a 0. Sometimes you'll get a 2. Maybe sometimes you get a 3. Okay. It's possible. It is possible, maybe not as likely to get a number higher than that, but know that on any given sample here that you do, you could get any one of those outcomes, all right? And so we just got to count the number that we got, and then what we'll do is we will collectively see how we do this as a class, okay? So as I move to the next slide, I'm going to go back to A, and it says carry out, using method A, carry out to find the number of winning game pieces amongst the 6 that you attempted with, okay? And so when we did this, I had 1 winning game piece. And so what I would do is I would fill this in. Okay, and then what I'm going to ask you to do as a student is to do it one more time. So take your dice, roll it 6 more times, okay, and see what you get, okay, and count the number of game pieces that were winners, okay. Now, when I did this another time, I got, for my specific example, 6, 2, 3, 3, 2, and a 4, okay. And so here I got none. I got 0 winners. Okay, and it makes me sad. There's my little unhappy face. That happens when you go to McDonald's, like, dang, I didn't win one this time. And you're like, do I even want to finish the meal? But I would have to fill this in too. Okay, now, that's just 2 game pieces, all right? Sorry, 2 meals with sets of 6 game pieces, all right? And I bet you have a set for your 6 as well now. When my class did this, okay, and I had my 5th hour class did it, I had 25 people do it total, I think, and I had them do it each twice, so they each had 2 sets of value meals worth of data. We ended up with this representation. Okay, so those are the total amount of winning game pieces that I had amongst my students in class on the simulation for part A. Okay, now, is it likely to get 3 or more? Well, let's see. One in my pen, I'll draw this in red so you can see it. Here's 3 right here. And if you want something higher than that, that's the 4s, okay? And I think there are 50 filled in items here. So if I were to ask, hey, is it a probability of the number of chicken McNuggets, sorry, the number of winning game pieces out of 6 being bigger than or equal to 3, okay? And let's make sure I define X here, is the number of winning game pieces okay, out of 6, okay, you'll find that we got 4 out of the 50, okay? And for now, you can just leave it like that. It's the reducing isn't as important to me, okay, because really we just wanted to create a simulation that demonstrated this situation, okay? And I didn't choose exactly 3. I picked 3 or more to kind of set up a moment or more extreme, okay? But you can see that's not very likely, okay? That's, yeah, 4 out of 50, so about 8% of the time, okay, in this particular case, okay? Now, if I did a different class, am I going to get a different distribution amongst my outcomes? Yeah, definitely. Will it look a lot different? Maybe, you know, it could. It's just that every time you have a new sample from your classmates, okay, or different people doing this activity, you're going to get a bunch of different outcomes for whatever reason, okay? And so, but this is what we got, okay? And it could be that your class has something slightly different, but in the end, this is kind of our protocol for finding the opportunity of getting 3 or more game pieces out of 6, okay? When we did our simulation, it happened about 8% of the time. In this case, it was exactly 8%, but we know that that's, there must be some flexibility in terms of this answer because it was just a simulation, and that's all. So, all right. Sorry to cover up simulation, but that's just where this slide ended, okay? Okay, so the next one, deal with coin flips. All right, and here's what I want you to do. Trying to find my mouse. There we go. And I have some definitions I'm going to talk about on the side in just a minute, but I want to do the activity first, okay? And throughout this slide, you're probably going to have to pause this recording just for a moment, just so you can finish the activity. Not that it's hard, but I just want you to keep track of your own work without having this video keep feeding, okay? So here's what you're going to do. You're just going to take a penny, okay? And you're going to use this table down here at the bottom to help record results, okay? And so all you're going to do is you're going to flip a coin, okay? Flip, flip, flip. Okay, record it and see I got a heads. Okay, so in our particular problem, we're going to record the number of heads that I get out of the total. Okay, and so in this first representation on here, you can see that down here, I'm just going to point to it so you can see where I'm at. I have a 1, and so I am currently 1 for 1. Okay, and I'm going to mark that on my chart here. There's a 1, and this just means, you can see here, number of trials. I didn't want to put that up here in the middle because I wanted it read well without the lines going through it. And I need to record 1 over 1 or 100%. So if my baseline is 0.5, okay, then what I'm going to do is I'm going to count by tenths. Okay, and I'm going to go in the reverse direction on the lower side as well, 0.4, 0.3, 0.2, 0.1, and 0. And that's as far as I need to go because I can't have a probability below 0 and I can't have a probability bigger than 1. Again, we'll talk about that in a little bit. Okay, but here's what I want to do. For my first trial, I have 100% of my heads. Sorry, 100% of my flips were heads. Okay, and then I'm going to flip again. And I got another heads. Okay, so now I'm 2 for 2. And so I'm going to write that in 2 for 2. And under the second trial, I'm going to put, again, 1.0 or 100% is represented there. Okay, and then I'm going to flip again. I did not get ahead, I got tails. Okay, so now I am 2 for 3. And 2 for 3 is about 66 2/3%. It's actually exactly that. So 0.66 is just an estimate right about here for 3. Okay, and here's what I want you to do. Use your own coin and do this 21 times and keep kind of a cumulative total of the number that you got representing heads over the total amount of coin flips that you have. And once you have these all filled in, then mark those accordingly on your graph and we'll see what happens with our representation of points. Okay, so I'm going to hit pause on mine just so that I can finish my activity and I'll let you do yours. And then we'll see how yours looks and I'll show you how mine looks. Okay, and we'll talk about some vocabulary after that. Okay, so let me pause this after I move myself out of the way. Pause. Okay, so here's what I got with my work. Okay, I did every single one of my coin flips. Okay, it recorded the number of heads as I kept doing new coin flips, all the way up to 21 coin flips, and I marked the respective points on my graph above. Okay, with the respective probabilities. This, of course, is probabilities of heads. Okay. Now, something to observe. First, let's talk about what a probability is. And most of the time when I ask people this, they give me the definition they've learned in a previous class. They'll say it is the number of successes. Oops. Number of successes, not off. Over the number of outcomes. Okay, and so, and not that that's wrong, that's true, but we're gonna have a little bit more sophisticated definition for probability as we take this college level AP statistics class. In this case, we're gonna define it like this, and I think the book does a really good job of defining it this way. It says the proportion of times the outcome will occur in a very long series of repetitions. okay? So there are moments when we do our coin flip where we get exactly 0.5, okay? So like right here, I'll put a star by it where the 4 is. I got 2 out of 4, okay? 2 out of 4 represents exactly 50%, and that's what you kind of anticipate when you flip a coin 4 times to get half heads and half not, okay? But is there a guarantee that that's gonna happen? Are you always gonna get exactly 2 out of 4 heads when you flip a coin 4 times? And the answer is no, okay? Sometimes you'll get 1, sometimes you'll get 3, sometimes you'll get the extreme, sometimes you get 0, sometimes you may get all 4. It's just part of the phenomena when you flip coins. You're gonna get many different types of outcomes when you add up the total number of heads out of 4. Okay, so I was kind of lucky; it gave me exactly what I was supposed to get. But when you consider for myself, for example, 6, and let's put another arrow with a double line here. You know, I didn't get 3 out of 6. In this case, I got 4 out of 6. Okay, and I represented that on my graph up here. Should be about 2/3. Okay. And sometimes that happens, okay? However, what I want you to take notice is that, and this is the important part of the definition, in a long series of repetitions, meaning as you keep doing this activity over and over and over again, you'll find that the proportion of outcomes that are successes, which in this case are heads, gets closer and closer to this number 0.5, okay, which is going to be your probability in this case. Okay, so that's how we're going to define probability. Okay, and again, just to restate what it is, the proportion of times that an outcome will occur. Okay, and the outcome that we're looking for is heads. Okay, in a long series of repetitions. Okay, and we just did this 21 times. You could really flip coins forever. All right, and the idea is that it should get close to 0.5 as you keep doing more and more of these repetitions, okay? And again, the 0.5 would be the answer for this. Okay. All right, some other things to keep note of with probability is know that, and we shared this a little bit earlier, that you can never have a probability lower than 0, okay? You can't have a negative probability per se, and it'll never be higher than 1, okay? 100 is 100%, and you can have more than 100% representation for any probability. Okay. All right. Second to last thing is this law of large numbers. It says in a chance process, the proportion of times a specific outcome approaches a single value. Okay. And these are a little bit related, probability and the law of large numbers, but it's the idea that says this in a chance process, and that means like you're flipping a coin or rolling a die using a spinner that's balanced and weighted nicely. It's the proportion of times a specific outcome you'll get approaches a single value, okay? And this single value that we're approaching is 0.5, but it's the idea that when you do more and more repetitions that it should get closer and closer to this value of 0.5, okay, in this particular case. In the beginning, it's very variable, okay? And this is just how mine looked. Yours could have been all over the place too in a variety of directions, but the law of large numbers says that as you continue doing this process over and over again, which means flipping coins, that is eventually going to hover around some unique value. And that's what this value is. In this case, it's 0.5. But it takes some time for us to kind of stabilize around that number with, again, a variety of repetitions. Okay. All right, last thing is coin flips. And I love this question because you get 2 different representations here. And keep in mind that order here does matter. Are you more likely to get heads, heads, tails, heads, tails, or 5 heads in a row? Okay. And oftentimes it lets students think about it and not trying to blow the question up early when I said that order has to matter. But most people think that this is the better answer. They think that, hey, I'm more likely to get this because it feels so hard to get 5 heads in a row, right? But when you think about the probability of getting a heads, which we said earlier was about 0.5 or a half, and I repeat that for this heads as well, and then we think about a probability of a tails, probability of tails is 1 minus this, which is a half, because you can only get a heads or a tails on a coin. Okay, you'll notice that these are all going to be, whether it's a probability of a heads or a tails, a half. So that's 1/2 to the 5th. Okay, and this is also 1/2 to the 5th because these are all a half. And so while some people maybe were comfortable choosing this as an answer, they're actually both the same. Okay, because they both have the same probability for getting each of the respective sequences, which is 1/2 to the 5th power. Okay, so they're the same. All right. If you have questions, and just going back to this, because this came into my head, remember that you may have had something completely different from what I had. Okay, it's kind of expected when you're flipping coins. No two coins will flip the exact same way. But in the end, my hope is this: whether you hovered back and forth along this 0.5 or eventually just approach the 0.5 towards the end, that's the idea. Okay, is that in the end you should get close to this 0.5 as you flip your coin more and more times. Okay, and had you flipped it another 20 more times and extended this out further, okay, I don't know how your points would have looked, but you know, chances are they would have just hovered around this and gotten closer and closer and a little bit above and a little bit below. Back, sorry. That's actually it. So in any case, if you have questions, talk to your teacher. My assignment is actually on the bottom of the note sheets that you're using for this. I would show it to you, but actually I'll do this. I'll keep it and I'll go back and show you the assignment. There you go. All right, so that's what I give my students as a homework assignment. Good luck with that. If you have any questions, holler at your teacher. Have a good day.